class. I'm going to start second part of chapter 3 today. Yesterday we learned that from scientists or start. Okay, so current flow through it will produce magnet, right? So this is what we call electromagnet. So after this all start, then come Faraday. So Faraday was thinking, can magnet actually produce current? Since that current can produce magnet, it should be both way. So Michael Faraday start to carry out his experiment by using this. He make a coil, okay, and then there is ammeter or milliammeter probably to determine whether there is something that can produce electric current. So he carried out the experiment like this. He actually changed once he fixed everything like this. He switched on. He found that hey, there is no current. So he changed to stronger current. Still no current. So he's changed to stronger magnet, but still no current. Then he carried out the experiment for many times. He changed the magnet, he changed the ammeter, and he changed even the switch. For many times, he found that there is no electric current produced at all. He repeated the experiment for 4 years. Okay, just a simple experiment, but he repeated for 4 years. There was once he's still doing the same thing. He forgot to switch off when he tried to change the magnet. Okay, so the switch is on, and then he see that no current, so he has to change a stronger magnet. So he pulled out the magnet. Once he pulled out the magnet, he found that there is current produced. So he put in the magnet again, there is current produced. So he actually came out with this conclusion: there must be motion, there must be changes to produce electric currents. So after that, Faraday actually came out with many type of electrical generator, but the one that very famous is actually we use this kind of magnet. Let's say this is North Pole and this is South Pole. So you can see that the magnetic field line must be from north to south, right? So he actually used a wire or copper wire. Then he moved the wire in to cut across the magnetic field line, and then let's say, of course, this must be a closed loop. Let's say you connect to light bulb, then it can actually light up the light bulb. Okay, so how to determine the direction of the current flow? Okay, so we have to use Fleming, okay, right hand rules. Fleming right hand rules. Okay, so Fleming right hand rule is like this. So this middle finger will be current. Okay, this is motion or force. We say that this always point towards south pole. Your pointer always point towards south pole. So since that this thing is moving in, so my thumb will pointing in, right? And then this one must be pointing downward, right? Okay, because south pole downward. So I can see that my current actually flowing in this direction. Okay, so when the thing is moving in, current flow in this direction, and when the whole wire is pulling out, the current will change its direction. So this is the first generator, or we said that the very original authentic model of Faraday's electrical generator. Okay, so you remember, when there is no current, we need to use Fleming right hand rules. So after that, Faraday came out with his very original electrical generator. Okay, this is of course a metal that it can conduct electric, and then it connected to ammeter. This is carbon brush. Carbon brush means that it is only touching to the disc, solid disc. So it only touching, it doesn't move around, but it is just stay static here, and then the disc will move around. Okay, so in the middle of this one, it connect to the wire. Okay, and then there is a magnetic field line pointing downward. Okay, so let's say south pole here, north pole here, so it will go downward. So this is the first what you call generator model. Okay, so you imagine this. Okay, let's say we take this as the cross-sectional area. Okay, and then by using Fleming right hand rules again, Fleming right hand rules, so you know that let's say this will turn towards our direction. So it turns toward our direction. So thumb will always point toward outside, right? and then the south pole is downward. Okay, wait, south pole is downward. So you can see that the current is actually flowing in, right? So it's flowing in. So when the current flowing in, it will come down here. Current will flow here. It come down, it go here, and it's go here. So this is the first DC generator, direct current generator. Okay, this is the first direct current generator. Focus here, focus here. 这个 empty 了，不要放。Okay, so this is what we call Faraday's first DC generator. So during that time, this Menteri Keuangan of England asking Faraday, why do we need this thing? Faraday said, you probably can collect more tax by using this. And now today we know that people actually making money by using this thing. Okay, of course, after that people modified it. Here comes another great scientist. We call it Faraday. Okay, so we call it Tesla. Okay, so Tesla and Edison is another kind of they have many interesting story. I would love to share with you if we have chance. Okay, so you see that this is permanent magnet, North Pole to South Pole, right? So North Pole to South Pole, North Pole to South Pole, like this. No problem, right? So Tesla actually put this thing here. That is a coil or a loop of, this is wire, huh? This is a loop of wire. And then he connected to two rings. One ring is here. Another ring inside, huh? Another ring inside, smaller ring inside. And then you have carbon brush here. Carbon brush means that it is actually only touching lah. It is not bind to it. Okay, let's say I put emitter or light bulb here, doesn't matter. So now we have to determine the direction of the current flow. Okay, for this one, if the current, if I turn the coil like this, it is moving upward. It is moving upward, right hand rules, huh? So it is moving upward, this one upward. And then you have to turn the pointer to south pole, right? So you can see that the current actually flowing this side. Okay, so as the current flowing this side, it will go like this. Okay, so this is the first loop of the current flow, and then it complete. Okay, but then when this thing turns to, let's say this is A side, okay, this is B side. When this thing turn to this side, the current will flow from B here, right? So when the current turn to B here, you will get alternating current, which means the second half of the motion, it will actually change direction. The current will flow in opposite direction like this. Okay, so because when A turn to B, and then B will get the current first, right? So it will turn like this. So this is how we produce alternating current. Okay, of course, in reality, this is not the model that we produce in electric current in our hydroelectric dam. It is much more complicated. The magnet is the one that turning, and also the coil, we have three loops together. Okay, my drawing. Okay, three loops together, which 120 degree to each other. Okay, so it can maximize the electrical production. Okay, now we go to graph. So this is the graph that we have for alternating current. Okay, so this is voltage and this is current. We can see that this is actually period, right? So our current that produced by Sarawak Energy is 240 volt and 50 hertz. Okay, 50 hertz means that the period here will be equal to 0.02 second, right? So 1 per 50 is 0.02 second. Okay, and this is not 240 volt, class. Okay, this is V max. V naught means that V maximum. So the current that we get is VRMS because it is sinusoidal graph, so it go up and down, up and down. So averagely we got VRMS, which is equal to V naught square root of 2. Okay, so we know that RMS that we get is 240, right? So what is the maximum voltage that we get? Will be 240 times square root of 2, which is equal to 340, around lah, 340 volt. So in terms to get 240 volt, and then we actually need to produce maximum voltage of 340 and 40 volts is quite high. Okay, so what is the factor affecting? What is the factor affecting induced EMF or induced current? Okay, what is the factor affecting? First, of course, the speed of relative motion. Okay, of course, if you cut through the magnetic field line more, you will produce more induced current. Second is the strength of the magnet. So we use stronger magnet. Okay, if you use stronger magnet, you have more line to cut off. Okay, and then number 3 will be the number of turns of the solenoid. Solenoid is the Hall loops. We don't use one wire to cut the magnetic field line. It is not efficient. So we actually use a loops. We call it solenoid. Okay, so if you still remember dynamo that we connect it to bicycle, not the dynamo that we use for washing your glove. So dynamo inside you have one permanent magnet and then you have wire. So the wire will come out and then it connect to light bulb. Okay, so this thing actually attached to your bicycle wheel, right? So once you start to cycle, actually you are turning the magnet. We try to avoid to turn the wire because it can mess up everything, hair wire. So we have to use, we turn the magnet. So once we turn the magnet, there are relative motion between the magnet and the wire. So it will produce a current. So what we call alternating currents. So there's another 2 things that you have to remember here. That is 2 laws under electromagnet. That is Lenz Law and Faraday's law. Faraday's law very easy. Faraday's law just state that the number or the number of induced EMF produced, voltage that produced, is directly proportional to the rate of change of relative motion. Means that you cut more, you get more electric EMF lah. Okay, so what is Lenz law? Okay, for Lenz law, you have to look at your notes. Lenz law is Lenz law state that Lenz law said that the induced current that produce, is flow in such a way that it actually go against the changes that causing it. It is some kind like inertia. So he refused to change. Wait, I'm looking for my Lenz law here. Where is Lenz law? Yeah, here. Right? Look at the computer. Okay. So Lenz law. Wow, cannot focus. Okay, Lenz law states that the induced current will flow in such a way that it opposes the changes that causing it. Okay, so this current that produce, we know that we are going to produce current, right? The current that produce trying to avoid changes. Okay, it's just like inertia, you don't want to change. If you are sleeping, you will sleep forever unless there are external force, right? So if you are talking, you will talk forever unless there are some people that stop you from talking, right? So same thing happen in electricity. So when you, let's say you see this thing, North Pole, right? You can see it clearly. This is North Pole. So when North Pole going in, when you push the magnet in, the magnet or the loop here will try to push this thing out. So how to push this thing out? Is by turning this side North Pole. So North Pole and North Pole will repel. Okay, so I repeat. So when North Pole going in, this thing try to reject North Pole. So he will turn these things as North Pole. Okay, so it will repel it. So North Pole means that it will turn anti-clockwise. So the current will flow anti-clockwise. Okay, anti-clockwise to make sure that this thing doesn't go in. But you still force it in, right? So when you put it out, means that this thing doesn't allow magnet to come out. So solenoid will turn itself to South Pole so that he can attract the magnet inside. So it's like kind of rebellion, like teenage, right? So you refuse to change. When magnet come in, you refuse to make it come in. Okay, so when magnet go out, you refuse it to go out. So you try to go against whatever it is. So what is Lenz law? Lenz law said that the current that produce, again, come here. Lenz law said that the current that produce will flow in such a way that it go oppose, it go against the changes that producing it. Okay, so Lenz Law, I will test. So what is the things that I have to highlight today? Okay, we come back. So what is induced? What is induced EMF or induced current? Okay, it's a current that produced when there is relative motion. Relative motion is a keyword. When there is relative motion between the conductor and the magnetic field line, which means if this is my solenoid, I have a wire here. So if it moves together, it doesn't produce any current. It only will produce current if there is relative motion. Okay, so first thing is induced EMF and induced current, you have to remember. Number two, what is the factor affecting? What is the factor affecting induced current? Factor affecting induced current. Okay, we have three just now I mentioned, and then number three will be Lenz Law and Faraday's law. Okay, Lenz Law and Faraday's law. Okay, and there is not really a calculation here, but we have only one formula just now. I means RMS equal to V naught square root of 2 and IRMS equal to I naught square root of 2. So there are 5 things that I'm going to test for this subtopic, that is induced EMF or induced current. Okay, thank you class. I will continue with the catapult next lesson.